Thanks for the intro. So yeah, I'm Andrus, and I'm the founder of Apache Cayenne. That we'll talk about Cayenne a lot today. So this is another project of mine that I'm doing, and I'm hoping it fills a gap somewhere between an ORM and some kind of extensive big data solution. So usually in our blood, we're working with ORMs for all our lives, right? So we model data one row at a time. So we take a row and make it an object, right? And we also model, we may not think about it, but we usually model like normalized data in a database. But this is just one small part of the data universe. And for instance, data scientists, they look at data differently because they need more flexibility than like anything like ORM can provide. So they usually model data one table at a time. So their granularity, their object is something called the DataFrame, and we'll talk a lot about data frames. And since I only have 20 minutes, I cannot delve deeper into difference between like ORM and data science and all that. But let me give you just one example where ORM ends and something else starts. And this is just a simple SQL query with a group by at the end. And the two important parts of that is a count in the select clause and a group by at the end. So what it does, it actually changes the nature of the entities that you're working with to something entirely different. So you have here like a department and an employee, and you probably have like entities for those. You have your EO model or Cayenne model. But when you aggregate them like that, when you start counting how many people work for this department, when you get this data set, it's no longer a department, it's no longer an employee, it's something else. So you just change the identity of your data, and ORM no longer applies, right? You can still probably model it as objects, but just consider that you can have a large number of transformations like this, a large number of aggregations, and you will need a separate object for each one of them, right? So this is where ORM ends and something else starts. So what everybody else uses in this case is a data structure called DataFrame, and it is used widely in two big areas. One is big data, where all the data about us, when we click on the internet, it's collected, it goes through a series of tubes and ends up in somebody's database. And this is where they start processing it, and it's like petabytes of information. You need to aggregate it and make sense of it. And another one is like more, data analytics, data science, where which is not necessarily big data. It, you can just analyze your sales in your company, but still, you will need to slice and dice your data in many different ways. And these people are using DataFrame, and DataFrame is essentially a table. So you can think of an Excel spreadsheet. So that's a DataFrame in a way. That's a very familiar structure. If you think of it, it's a table, but somehow it is present in like R. It is present in Python, in the form of Pandas framework. It is a central part of Spark. But we as regular Java developers, we don't have anything like that. So we model data differently. And we try to work around the limitations of our model. So I'm thinking that by introducing a data frame in Java, we can, as a part of, as a goal of the DFLib project, we can actually, take advantage of all these approaches that data scientists are familiar with and, using all the time. So let me show you some code, and let me go quickly because I only have 20 minutes. So DataFrame, unlike ORM, you can create it from anything. So any kind of data that you have. So here I have a one-dimensional array. I fold it to create a two-dimensional array, essentially, and DataFrame is a two-dimensional array. But and the important piece actually, so I wanted to show like how you print it, because the following slides will actually use this tabular printer, the last line, so that it shows a table of data. So it kind of helps to understand what's in the data, because data is like, it's a sequence of something, and it's really hard to understand what's there, so the printer is important. The following slides will use it implicitly. You can get the same data or some other data from a database. And like I said, the source doesn't matter. All you get is a two-dimensional structure. You get an in-memory table. So you can run a query and get a data frame from a database, or you can get it from CSV. We just mentioned CSVs in the previous talk. I mean, CSVs are important and in ways that you can easily export it from Excel, for instance, and then you can feed it to your data analytics program or something. So CSV is a common, simple format, and unlike the database, we don't know the data types in CSV. It's all strings, so we may need to give some information, some extra information, so that the columns are the right Java data type. And this timesheet data frame that we have here, I'm going to use it on the following slides because it's a simple model. We're a consulting company like Object Style. We have about 70 developers, and we all fill timesheets so that we can bill our clients. So the model is kind of simple. I think everybody understands it. The first thing you can do with data frame once you loaded it, you can actually throw away the garbage. You can throw away the things that you don't need. So you can say, okay, I only need these columns, and the rest, it's for some other task. For this task, I only need just a couple of columns. And same thing with the rows. And you can actually specify the order of the columns. You can duplicate them. You can put the same column twice or the same row twice. And at the end, you get the data set that you can work with. So this is like your basic preparation. You got data from some data source. You need to clean it up first. Now more interesting pieces where you can actually transform data in the column. So we had a person name, and we can split it into two columns, first name and last name. So we can apply some function which is, it's not on the slide, two first name and two last name, it's just some custom function that takes a string and returns a string, right? We create these two new columns in the data frame, and at the end, the last line, we drop the person name column. So it's very simple, and you can do it with objects because all your fields in the object are predefined, right? So in data frame, you can add, remove columns and rows. And another important piece is data frames are immutable. So all these transformations, they create a new data frame. So every single column, add columns create a new data frame, drop columns create a new data frame, and every single operation that I will show you further down. Which is important for a number of reasons, because first, concurrency, because you can operate on the same data frame in parallel in as many threads as you want, and second, just your sanity in general, because mutable data structures don't help you with your mental health. And of course, just like any data technology, the first thing you want to do is to filter and sort it. Of course, it's there, you can do it. But here's an interesting thing. It also supports joins. So this is one of the things that it supports that actually distinguishes it from, like Java 8 strings framework, for instance. So here you can actually take two data frames. I'm loading a second data frame, which is consultant rates, right? So we have a timesheet and we have how much an hour of a consultant costs to the client. And those are two different CSVs or two different databases. It doesn't matter where it comes from. And we can join them together. As a join syntax, we're going to shorten it a little bit. This is still the first version. But it underscores the algorithm behind the join. In databases there are two algorithms for joins, like hash joins, which are fast, and nested loop joins, which are slow. And you may not think about it when you're doing a join in a database, but you are actually doing probably a hash join. Here you have your mini database. So DataFrame is your little database that you have in your application without any infrastructure. So it's just a little object that's also a database. If you see on the previous slides, there's a column that doesn't belong there. So the person name was underscore. It got there because it wasn't both data frames. When we joined, all the columns were preserved, and one of them got renamed to avoid a naming conflict. But obviously you don't need that. It's a duplicate. So here is a version where we actually drop it at the end after the join, and we get a nice and clean result of the join. Aggregation. So I showed a group by example before. So here's how you do it with DataFrame, and it's a little loaded. So first we actually, before we do aggregation, we calculate the revenue column. So we add another column to the data frame where we multiply the hours by the rate, and we get how much money the client is going to pay for this line item. And then we aggregate, how much money each person on our team makes for the company by grouping by person name, and the group method. The group method actually returns something that is not a data frame. So everything else was like returning data frames. This one returns an object called group by, which is it's a map of data frames by the grouping criteria, by person name in this case. And the last line is turning the group by again into a data frame, but a different data frame. It's a data frame with aggregated data, so that's our end result, and it includes the person name and the revenue. So this is our, we're following everything we can do with SQL here in Java, in memory, without any storage, window functions, I don't have too much time, so I'm probably gonna just skip that. I mean, essentially, so window functions are using analytics, and all the database engines that claim analytical capabilities. They have like the whole list of window functions that allow you to do some analytics within like parts of the result set adjacent to a row you're looking at. So we're also getting into that space. But I won't delve into the example. Performance. So of course, everybody, when they have lots of data, they go into this like cluster solutions like Spark, that requires like Hadoop and all the crazy things that require like the whole team to maintain, even if it's in Amazon or something. So here we're talking about like in-process data processing, like a single process that works with your data, but so it has to be efficient. So the 2/3 of time on this project I spend on like index and integer arrays and like just doing some pretty low level from the Java perspective operations, because you can't do real low level in Java. So you have to work with what you have. So you can fit about 38 million long cells in a gigabyte of heap space. So you can make a calculation. If you can have 100 gigabytes, it's 100 times more. So you can actually work with pretty large chunks of data using this technology. So I'm thinking about it as a technology for like medium data as opposed to big data. And the performance. So here's the performance, and I have two columns: version 0.5, which is a current release, and 0.6, which is in development. The performance is decent from the start, but it's improving, and that's a good thing. So we're finding like new ways to make it faster. So it's only going to get faster. Like the last two columns, like the last two cells on the right column. Actually, this is a result of what I did on the plane when I was flying here. So it improved about like from 25 to 50%. But a join of two data frames of 1 million rows, it takes below 100 milliseconds. I think it's okay. It's not the database speed because Java, but it's good. And like once we move in from like Java wrappers for numeric objects to just primitives, we're getting to where probably guys like Cassandra are. And you can do it in your Java application. It doesn't require Hadoop for it to run. So future development, we would like to make it a little more friendly for Java developers. If you've seen on the previous slides, I have some casts. When you get a value out of the data frame, essentially it's just like getting a value out of an object array. So you have to cast it, which is not nice. So we'll probably provide some extra metadata facilities to make it flow smoothly. The core of it's actually the functions, because by itself the data frame is just a two-dimensional array. It's not exciting, right? So the exciting thing is what you can do with this two-dimensional array, and this is where all this like statistical, analytical, geospatial, time series functions come into play. And this is why people are using Python and Pandas, not because it's fast, but because it has all these packages readily available. So we're gonna work on that so that you can do more with this data, in addition to emulating SQL and doing joins and group by, which is great by itself actually. Further performance optimization, of course, we are moving from object wrappers to like primitive numbers, which is like a real pain in Java, but since we already have everything hidden behind the data frame, we can actually, we can sustain this pain as DFLib developers so that you don't have to. Notebooks is actually another concept that is totally unfamiliar to Java developers, but it's great, and it probably warrants its own its own presentation. So here I just mentioned it. So it's a way of like visually develop the data sets where you make an operation, you see what happened visually. Then you make another operation, you see again what happened. So like, finally, just use it as an engine for unit tests. Because I spent like literally months developing technologies to like compare data sets for for Cayenne, for instance. And when I'm writing a unit test, I want to see that the data that got saved in the database is the correct data. I need to compare it with something. And DFLib actually will invalidate all that work that I've done, and I can just do it with DFLib. And finally, some advice on where you can use it. So if you're moving data from system A to system B, and this data does not have any like business descriptors for you, it's just data, and it's a bunch of intermediate states. You don't want objects for those states. You can just use DFLib. It's generic. Aggregating, transforming, or calculating data in memory. How often have you written like maps of lists of sets where you combine your data and then something comes in, something comes out, but you don't understand the structure. It's like something you can't visualize it. It's hard to debug. And how do you know that you are writing the right type of join? That you are using actually the hash join and not the nested loop join, which has a n factorial performance. So also data sources. So it's agnostic from from the perspective of where the data comes from. It can come through the wire, database, CSV, anything really. You can have a random number generator and generate data frames for some simulation, for instance. And if you have data scientists on your team and they develop some models and they bring them to you, and now you as a Java programmer you need to put it in an application. That's a way to actually talk their language and program it the way they did. So that's DFLib. Yeah.
Right, so we got 2 more minutes for questions. So.
Okay, I've heard you saying pain and Java in one sentence at least 5 times. So why did you write it in Java?
Because I needed a solution in Java. So essentially, if I write it in C, I won't be able to use it, in Java easily either. So essentially, I think all those technologies where people knew how to do it low level with some direct pointer arithmetics, they already did it. There are already solutions there. So there's no solution in Java, and maybe for that reason.
This is about SQL syntax, because having created Scala Spark at one point, you can switch to SQL syntax when you want to.
Right, absolutely. So in Spark, for instance, you can use SQL on top of DataFrame. So this is the first release. So in the future releases, I think we might go there, and just because all this maps to SQL directly, essentially, right? So writing a parser for some SQL syntax. It's a fairly trivial exercise. I'd say it will support it.
And another question, so besides the join operation, do you support all the Java collection operation?
As a Java operation?
Java collection libraries operation, so...
Java collection libraries, okay. Okay, so... yeah, there are operations like concat. There's a vertical concat and horizontal. You can append your data frames to each other in this direction. There is also a map operation where you just pass any function and it reassembles the data frame from scratch, essentially. So you can. I was showing actually functions that are more useful, but there's some generic API where you can do anything from anything, essentially. If something is missing, of course, but we definitely need to expand the library. Let's put it this way.
Do you intend to have it work on your machine, or maybe in the future have it distributed?
We're not looking to have a cluster. Is cluster awareness. So essentially, it will be a goal of it will be something that your application will need to do. Like for instance, if you have an endless stream of data, you can chunk that stream into 1 million rows at a time or something, and then you can split it to different machines. So it's not in the scope.
Okay, so. Thank you very much.